Hello, we are Group 2 and we had the topic of electromagnetic and ultrasonic flow meters. The members of Group 2 are Darcius, Curtis, and Brian. In this video, you will see how electromagnetic flow meters work and then hear the pros and cons of electromagnetic flow meters. Then a video on ultrasonic flow meters will be shown, followed by the pros and cons of that type of meter. Finally, we will discuss the equations that are used for the flow meters, such as the Doppler effect and Faraday's law. The flow meters measure the velocities of flowing liquids inside of a pipe. Transit time ultrasonic flow meters use the principle of sending and receiving ultrasonic signals. The velocity of the liquid changes the transit time of the signals. This change in time is used to measure the velocity of the liquids flowing inside of the pipe. Doppler ultrasonic flow meters work due to the Doppler effect. A transducer emits an ultrasonic beam into the flow. Air bubbles or solids in the liquid shift the frequency of the beam before being received by the second transducer. These shifts are proportional to the velocity of the liquid. Now we will go into more depth on electromagnetic flow meters. Electromagnetic flow meters work on the basis of Faraday's law. A magnetic field is cast across the pipe, and as the liquid moves through the pipe, it is creating a voltage. This voltage is used to calculate the velocity of the liquid inside the pipe.
Beginning with how electromagnetic flow meters work, two field coils are located inside each flow meter with the help of what are termed pool shoes. These coils generate a constant magnetic field over the entire cross-section of them. Two electrodes which can pick up electrical voltages are installed at right angles of each other in the wall of the tube. There is lining fitted on the inside wall which prevents electrical short circuits in the conductive liquid and the metallic tube. If there is no liquid flow, no induced electrical voltage is measured at first between the two electrodes. The electrically charged particles of the conductive liquid are evenly distributed, shown here in water, with red and blue particles. As soon as the liquid starts to flow in the measuring tube, the magnetic field applies a force to the charged particles. As a result, the positively and negatively charged particles in the liquid, which are separated and collect on the opposite sides of the tube wall. Now an electrical voltage forms, which is detected and measured by the two electrodes. This voltage is directly proportional to the flow velocity in the pipeline, together with the known tube cross-section, and now the flow volume can be calculated.
The pros for the electromagnetic flow meter are as follows. No moving parts or flow obstructions, almost zero pressure drop, since the coefficient of friction for the liner materials, Teflon, may be lower than the actual piping material that they may provide less of a pressure drop than the same length of piping material. Accuracy is to plus or minus 0.25% of the reading. Flow range turn down of 300 to 1 or better. Available for pipe diameters from 1/10 of an inch to 120 inches. Relatively unaffected by viscosity, temperature, and pressure, as long as the magnetometer is selected based on the process conditions. Applicable to all flow profiles and does not require a straight run. Can respond well to rapid changes in flow. Applicable to liquids with heavy particulates. Available in a wide variety of communication protocols. Ability to register locally, remotely, or to interface with an energy management system. Service life of 75 years. The cons for the electromagnetic flow meter are as follows. Water must contain a certain amount of microsiemens, giving it the power to conduct heat and or electricity. Some magnetometers can work down to 2 to 3 microsiemens per centimeter, while others require 10 microsiemens per centimeter or more. Accuracy may be affected by the airspace in the pipe.
Inside the ultrasonic flow meter, pairs of sensors are fitted across from each other in the measuring tube. Each sensor can alternate between sending and receiving an ultrasonic signal. The times between these signals are measured. The ultrasonic signals are generated by electronic crystals that apply a voltage and create voltage when they are impacted by an ultrasonic signal. By increasing the number of sensor pairs, it is possible to accurately detect flow profile distortions over the entire pipe cross-section. When there is no flow, the signal times are the same upstream and downstream. Once the fluid begins to flow, the ultrasonic signals begin to accelerate in the direction of the flow and slow down against the flow. As a result, the ultrasonic signals have different transit times, less time with the flow and more time against the flow of the liquid. Therefore, the times measured by the sensors is directly proportional to the flow velocity inside of the pipe. Together with the known cross-section, the actual flow volume can be calculated. The greater the time difference, the greater the flow velocity. For ultrasonic flow measure, the sensors do not have to be mounted into the pipe. With a clamp-on system, the sensors are attached to the outside of the pipe. With clamp-on sensors, the ultrasonic signal is passed through the pipe wall and into the fluid and reflected on the opposite pipe wall and measured by the second sensor. The clamp-on design allows for pipes of up to 4 meters to be measured. Next up, we will discuss the pros and cons of ultrasonic flow meters.
Starting with the pros, there are much lower costs associated with installation, as your system would not need to be shut down and your piping would not need to be altered. The device will not obstruct flow or contaminate processes. The lack of moving parts means less maintenance. The flow range is typically 100 to 1. It can be used with corrosive fluids. There is almost zero pressure drop. It can operate on pipes of diameters from 1/2 inch to 200 inches. Insensitive to changes in temperature, viscosity, density, or pressure. It is available in a wide variety of communication protocols. And it is available to register locally, remotely, or to interface with an energy management system. On to the cons. Ultrasonic flow meters become less dependable when the flow rate drops below 2 feet per second. Any number of unknown internal piping variables can shift the flow signal and create inaccuracies. The scaling, pitting, and fouling that occur over time in older piping systems can become problematic. Accuracy may be affected by airspace in the pipe. And lastly, accuracy may be affected by the size, distribution of particles, and any relative velocity between particles and water.
Ultrasonic flow meters use reflected ultrasonic sound to measure the fluid velocity. By measuring the frequency shift between the ultrasonic frequency source, the receiver, and the fluid carrier, the relative motion are measured. The resulting frequency shift is named the Doppler effect. This can be used to calculate the fluid velocity by using the formula on the screen and in your handout. With time of flight ultrasonic flow meters, the time for the sound to travel between the transmitter and the receiver is measured. This method is not dependable on the particles in the fluid. This can be used to calculate the fluid velocity using the formula on the screen and in your handout. Magnetic flow meters work based on Faraday's law of electromagnetic induction. According to this principle, when a conductive medium passes through a magnetic field, a voltage is generated which is proportional to the velocity of the medium, the density of the magnetic field, and length of the conductor. Electromagnetic flow meters use Faraday's law of electromagnetic induction for making a flow measurement. Faraday's law states that whenever a conductor length moves with a velocity perpendicular to the magnetic field, an EMF is induced in a mutual perpendicular direction. Thus, the volume flow rate is proportional to the induced MEF. The formula on the screen and in your handout can be used to calculate this.